Welcome to Drone System and Control course. In the last lecture we talked about scenario generation for UAV operations. We talked about model in the loop, we talked about software in the loop, hardware in the loop, why those are important. When we talk about a specific mission and develop algorithms for that particular mission, we need to verify whether the hardware which is present can execute it at a specific frame rate, right, or execute it in real time. So for verification is also important. So how we can use different tools to verify those software is what we discussed in the last lecture, right. So we will be continuing about autonomous drones, model in the loop, software in the loop workflows. We talk about how we can create HIL scenario generations, and we look at various examples, at least 4 examples I'll run through how you can use MATLAB to generate different scenarios and how you can use those scenarios to verify and visualize the performance of your algorithms when we go for navigation or path planning or obstacle avoidance or autonomy perspective, right. So in the last lecture we talked about how to build the model for a quadcopter. Here I am just taking it one step further. The input basically comes from ground control station. The ground control station will define what is the map where you have to start, how you are going to navigate for a specific mission. All that will be present in the ground control station, and that will be translated as an input to the software in the loop simulator, right. Once that's put into the simulator, your flight controller comes into picture. The flight controller looks at the flight management module, which will see where to do takeoff and then go from point to point navigation, which we will be covering later, and then how control is going to execute, whether you want to fly in attitude mode or you want to fly in a velocity mode, velocity tracking or position tracking. Based on that, the flight controller will switch, and then the output of the flight controller goes to plant model, which we have discussed in the module 2, how we can represent the plant, and output of this plant will have a sensors, and that sensor will just come in. We check everything in the software in the loop execution, and we can port it into C++ on a host PC and verify whether the whole mission is executable in real time, right. Now software in the loop, we can add a PX4, right, and Simulink plant, and we can verify. So the flight controller can be just defined as explained in the previous lecture. You can just say I wanted to go to specific height, then you can just use the command what height you wanted to go, and then once you go what trajectory that you wanted to execute, right. You wanted to track a specific trajectory, then you can just check how Simulink model can just track a specific trajectory, integrating directly with the PX4, and that you can also visualize simultaneously in the software in the loop with the PX4 HSP, right. So more detail about how to monitor, how to tune the PX4 host for a target flight controller with a Simulink based plant, you can just go into the link. This link will be posted in our folder, which has a clear details about how UAV toolbox can be used and how you can define the commands, right. Commands like takeoff and going to 2 meter altitude. Once you go to 2 meter altitude, then I want you to go in a circular motion. All that will be created in the Simulink, and you can just pass on the reference command directly to your trajectory tracking module, and the trajectory tracking module will be executing the responses through PX4, and the plant is our mathematical model built in Simulink, right. You can verify and visualize the same in MATLAB. Now just more detail how this flight controller software in the loop, just to give you, it is the whole video of the same is available in the content package, which will be posted later. I am trying to explain the steps alone. So what we have is a demo flight controller loop. In the demo flight controller loop, we have hover mechanism, and we are just defining what altitude at which the drone need to hover. Here the quadcopter was considered, right. What is altitude? It's a sliding bar. You can use the sliding bar to just vary the altitude, and that command will be sent to the controller. Then the flight controller will just take that command and produce what is a thrust required and torque required, and that thrust and torque requirement will be sent to our quadcopter plant loop, which will run, and the output of the plant connected to the sensor. Sensor is again just outputting to visualization aspect of it, where we are looking at X, Y, Z. Instead of saying X, Y, Z, we are giving it in a global coordinate frame, north, west, up, right. So you will be able to see the navigation of the drone in a 3-dimensional plane. Now I am combining the whole system so that we can understand how physically all are going to be connected. We have a ground control station which is going to take the input. Again, I am just trying to give you an understanding. This is where your missions are planned, right. Based on a specific application, you are planning the whole mission, right, and the entire mission is planned, and you just say I wanted to take off at one particular latitude, longitude, and go to specific height and move from point A to point B and point C and deliver something and return back. So once you plan the mission, you are connecting the mission to your flight controller. The flight controller now have the entire mission, right. Now this is where initial connection take place. Once it has the mission, your flight controller model, right, whatever which is going to be present in the hardware in the loop, that model is present, and the model in the loop we can use, and output of the model can be connected to the plant, which we can verify, right, and the output of the plant which is basically connected to sensor, and sensor goes back into the model feedback, right. This is what your software in the loop part of it verifying. Now what we can do is we can remove the model in the loop, replace it with hardware, PX4 hardware. Last lecture just I explained what are the important aspects, what you need to disable and enable, right. For example, I do not have actual sensors connected to the hardware, so I need to disable the sensors and use data coming from the software, and soft sensors are going to be used in the hardware, and hardware runs just the flight controller. So we verify the flight controller part of it, whether my flight controller can run in real time in this hardware and provide necessary command to my plant, right. I can, instead of using this hardware, I can also do it in a small PC. I can convert the entire model in the loop as a exe file and just run it in a PC to check whether the PC can connect. So we can have either these two versions of it to verify. What we need to understand is whenever we bring in the hardware, simulator communication with the hardware we need to take care, because the sensor data has to be sent to the hardware in a specific form, and the simulator communicates with the host PC, right. So that also we need to take either this or this, right. When you talk about software in the loop, you want to do and convert everything, you need to know how the simulator can communicate with host PC. The communication aspect has to be figured it out, right. One step further you can do, you can connect a radio control and connect directly to PX4, and radio control can just give real time command directly to PX4 in case you wanted to modify the predefined mission in middle of the flight. You can just try to do and simulate whether that communication is taking place or not. Those kind of verifications are possible once you have this setup, right. So how do we do? How the communication happens between a PX4 and Simulink? We are going to use a MAVLink protocol for data communication, and that is going to happen through serial port, and we connect this into USB of a host computer, where the UAV dynamics is going to be present in the Simulink. The output of this dynamics we can send it to the Q control system, which is basically MAVLink. This is basically your mission planner, where we will be receiving RC data, right. Actual drone when it is flying, in real time it will send the states of the system including the battery directly to your ground control station, right, and that uses the MAVLink UDP protocol. We can use the same protocol to send the data to ground control station, so you can verify the performances also, right. The flight controller which was present in the Simulink, we can deploy the flight controller entire autopilot from MATLAB directly to the PX4 hardware, right. Once you deploy this model in the loop into the hardware, your hardware is going to be connecting directly to your dynamics and visualize. So here we will be able to verify whether the flight control architecture what you have developed, is it working in real time, it has any issue in communication, right. In the next stage, if it is possible, you can just take, instead of plant and dynamics, you can at least take the motor propeller directly and get the thrust information, and that thrust information you can bring it back to UAV dynamics loop, and rest of the thing is possible. There you can verify even the PWM command coming from your PX4, whether it is driving the motor properly, are you getting the thrust in a thrust bench, it is possible. Okay. So this setup will help you to visualize and analyze the performance of the flight control architecture that what you are building, and also the mission plan that what you have done, whether the specific drone is capable of executing the mission, what is the deviation in the mission performances, all that can be evaluated easily with this UAV simulation workflow with PX4 and Simulink, right. You can go one step further, you can get a beautiful hardware in the loop with scenario visualization. We talked about different scenarios, how you can get it, and you can have the scenario where the drone taking off between a building on the road and going straight to a specific location and drop the payload and return back. So you can verify the entire scenario whether it is being executed properly, what is the performance of the drone in those scenarios can be validated easily in MATLAB interfaces, right. If you want to read more about the scenario generation, and you can go into the product page or you can look at the overview. UAV toolbox I suggest everyone to go through. This particular toolbox has a PX4 autopilot. As mentioned in the previous lecture as well as in the current lecture, the PX4 autopilot toolbox has sensor models, right, IMU, magnetometer, gyro models, right, altimeters. You can use LiDAR also, you can integrate that, or radar altimeter. All this can be taken from this particular package and you can directly connect, right, and GPS also is available. You can connect so that you can emulate the hardware and you can verify everything at least in the software in the loop structure, right. More documentations are available if you go into the www.mathworks.com/help and UAV. You can see quite a bit of documentation. You can understand from there also. There are examples available if you go to that particular page. For learning more, right, the platform development part of it, we have covered quite a bit of dynamics model and how this dynamics can be visualized in Simulink. You can just create the same. You can do motion planning and control. Basically you can define your UAV mission. You can do the path planning, RRT star or Digistar, A-star path planning, global path planning. You can do that. We will be covering different path planning algorithms, A-star, RRT star and all that. You can use one of them and create the path and see whether your drone is following the path or not, and you can evaluate the performance of it. Some advanced control, what we covered in the lecture is state feedback and PID. If somebody wants to implement advanced model predictive control or neural network based controls, if you want to implement, you can still do it. You can implement them in Simulink and then deploy directly into it. I will show you in one of the use case in the last module when we talk about autonomy, how we can use neural networks directly and then deploy them also into PX4 structure. The scenario generation is what we have covered. There is quite a bit of online resources available. That's not in the scope of the work to talk about how you can do that. Right? I am just giving an introduction to the scenario generation in this particular module. If you want to understand more about how to generate the scenarios, how you can go more realistic, photorealistic simulations like what you see here, right? You want to go more photorealistic simulations you can do. You can also interface directly with the Unreal Engine, and with MATLAB being running the physics based model and Unreal Engine showing this visualization of it, it's possible. Right. This perception and planning part, right, we'll be covering in the next module when we talk about autonomy. We talk about how we can use camera as a sensor, and using the camera you can identify the objects and then you can do obstacle avoidance if you want. And you can also use camera to do object detection, so we will talk about it. Right. So you can read more about perception and planning. We will just give an introduction to it, and if you are interested you may have to take courses on aerial perception, which will give you a lot more understanding about object detection and tracking, which is possible using multi-sensor fusion or estimation. You can use Kalman filter to estimate, right, or you can get into deep learning based image classification, future learning kind of a thing. We will also give an introduction to simultaneous localization and mapping, right, and you can use LiDAR as a sensor to do simultaneous localization and mapping, which is called SLAM, or you can use visual sensor, which is a camera based sensor, to simultaneous localization and mapping. You can read more about it when you go into perception and planning, which is very important factor in autonomous aspect of it, which we will be covering certain components of it in the next module, okay, introductory part of it. This is a course by itself, perception and planning. Okay. Now I will take you through some simple examples how to generate a typical scenario using polygon as a building meshes, and I will also show you how you can use polynomial trajectory using UAV, and you can create and simulate the UAV scenario. There are a scenario designer app in MATLAB, how you can use the designer app to create a scenario and go ahead. I will show 4 examples, and that particular MLX file will be uploaded into the folder for everyone to go through and visualize. Right. Now let me show you how to create UAV scenarios in MATLAB for visualization purpose. Right. I can create a scenario using polygon building meshes. The first step I do is I call the function called UAV scenario, and I can define the update rate that we are looking for, and we can define the reference locations where you want the scenario to be generated in the whole plane. Right. Then you can just define what is your ground plane. You can load building polygons. If you already know what the size of the building you wanted to add, you can just create all the polygons separately. You can load them, and then just like that you can show it on the plane. Right. You can define colors for a polygon. You can say what is the color you want for the plane. Here we are defining the color for the plane is gray, and we want color for the building to be green, and we will use red as a point where we can just start. So I create the mesh. The mesh is just 250 cross 200 and 150 cross 200. Right. So I have 0 to 50 meter. So buildings I am just adding on. I already created a mat file, the building.mat file. Basically a different size building. Some are L shapes, some are a rectangle, right, some are square. So I created the building, and that particular building I am loading, right, and then every building I am just trying to say where the building should be located, what's a polygon it is, and then I can add all of them and say now you show the 3D scene, then it will show the 3D scene. right? You can define what is your x limit and y limit of the 3D scene so that you know all the distances clearly shown in meters, right? This is one way of creating a scenario. The other way of creating a scenario is you can just go ahead a scenario and add an inertial frame. You can say I don't want to do it here, I want to use an inertial frame and a map, and then I want to create a scenario on this. You can say what is your frame rate, update rate that you want, how much time that you want it to run, stop time, and then reference location where the scenario need to be created. I am just giving the reference location where I want that scenario to be kept, right? Now, then I can use a function called min jerk poly trajectory function. This is a piecewise polynomial for a specific waypoint. You can give a waypoint and it will just create multiple sub waypoints, and with that it will fit a piecewise polynomial, right, and it can generate a trajectory. So here I am defining a waypoint. I am saying 0, 50, 100, and then I am saying 0, minus 50, 100 and 0, 0, 0. 3 different waypoints I am giving, and I have to say what time I want to be in this 3 different waypoints. That is my time points or time stamps that I wanted to reach. I am starting from 0. The first waypoint is at t naught is equal to 0. The second waypoint is I am just giving 3.8596 seconds, and third waypoint to be reached in 11.4451 seconds, right. So you can define exactly the timestamps that required for different waypoints and how many samples that you want between these 3 waypoints. Then you can just pass those 3 inputs and that will generate your trajectory, right. Once you have the trajectory, that is PP, and you have the sample rate, then you can just pass on directly polynomial trajectory as a function, right, and you can pass on that information. Then you can create a UAV platform and specify the polynomial trajectory in the scenario, right. This is my UAV platform. It is a custom. The scene, I am just a custom scene that what I created, and I can say this is my trajectory. Then I can keep updating my mesh so that I can see. You can use a fixed wing or rotary wing. You can pass on based on what is needed, right. That is another way of creating a scenario, another way of showing the trajectory of this whole drone in the 3D space. You can do it also with UAV scenario, right. You can define your inertial frame, how do you want that, and then you can add a mesh and 2 cylindrical obstacles in the whole scenario. I define one as a polygon is my whole area, and then I am defining 2 cylindrical obstacles located at a specific locations, and then I created a UAV platform with a waypoint trajectory that what we talked about. I said this is quadcopter which is going to fly, and this is what it is. Then I can say I am attaching a INS sensor, inertial navigation sensor, which means I have accelerometer and gyro, and the output of those 2 connected to my extended Kalman filter, which estimate the states of the system. So I have that information. Now I can say I want to visualize the whole thing. So you see here I created 2 obstacles, 2 cylindrical obstacles and then I can run the whole simulation here to see how the UAV crosses the obstacle, sense the obstacle with the sensors whatever available. So we can, like this, you can create a scenario in which you wanted to test your system in a 3D plane, right. The best way to do is use the designer app, right. Usually we use these kind of scenarios when we are talking about systems where we wanted to test just obstacle avoidance, we just wanted to check, right, we will do that. But if you want to do it final visualization and validation, you can get into UAV scenario designer app, right, which will give you a lot more choices. You can define how your polygon is going to be, right, you can drop down and then you can choose whatever polygon you want, whatever the size you want, you can define in the app. Then it will create beautiful polygon which is exactly showing in a 2D plane, right, which is y and x. And then you can get a 3D visualization here and how your polygon is visualized here. So you can define that straight away using the app. that will be easier. You can add a platform, whatever platform you want. You can say I want to have a fixed wing or a rotary wing, and I want to visualize the quadcopter flying in XY plane. You can define that straight away from the app, and then you can visualize in a 2D as well as in 3D here, right. So it's possible directly using the designer app. You can add sensors to it, right. You can define what kind of sensors you want, and you can integrate you can define the ranges of the sensors when you add what's the sensor you are adding, what is the minimum range, maximum range, what is the accuracy you need. Everything you can define in this designer app, and you can visualize them in 2D as well as 3D plane, right. So then you can create a trajectory. You can simulate the same thing like what we did, and this is my terrain, and use this terrain. I can use any model which we have pre-built where the buildings are available. I can port that particular model as a scene, right. Once I port the scene, I will show you here. This is a 2D view of that particular city location, and this is how the buildings are located, and these are the roads. You can see the same 3D view in the picture. This is the buildings located, and I can fly in this particular scenario, right. So it's easier for you to visualize by adding a sensor, adding a scenario, and run the simulation and verify your performance using the designer app also, right. This is a trajectory. I can choose a fixed wing, I can choose a quadcopter, all that I can do. I can define where the quadcopter should start, at what position it has to be. So you can define the platform, you can define the coordinate frame, and you can just say where at what elevation it has to be present. You can define that very clearly, right. And if here is fixed wing, it will show as a fixed wing, and if it's rotary wing, it will show as a rotary wing. So you can use that specific system, and then you can add waypoints. If you go to trajectory, you can add waypoints. These are the waypoints I want the system to follow. The aircraft is here, and the first waypoint, second waypoint, third waypoint, and you can use a polynomial fit to generate the trajectory and pass that trajectory to the flight controller, and the flight controller will execute the trajectory, right. So you can visualize the same in 3D plane too, right. The aircraft is here, is going through this particular path, flying all along the road to exit to the other side of it, right. So you can visualize, and we can also evaluate the performance, and you can look at how the altitude autopilots work. If you say I want to keep a height of 126 meter, let's see whether it's holding the altitude or not, right. So based on the previous module, we talked about flight control architecture. Altitude hold means you will just keep the height being constant, and then you will try to keep XY to be tracked, and then you will just generate the velocity command. The velocity command will go to your attitude and then rate, and finally it will give you what kind of RPM needed to generate the thrust and torque, right. So that part will be executed by the flight controller. Now in this particular module, we are starting with the scenario generator as an introduction to understand, because the mission need to be defined based on the application. Mission defines where you need to start, what you need to do, where you need to end, right. Then your navigation algorithm comes into picture, which talks about point to point navigation, how we are going to do point to point, different points, how we navigate, or we talk about the entire path planning itself, with obstacle being present, static obstacle being present, how do you plan the path, right. That is a global path. Then we have obstacle avoidance problem comes into picture. How do you handle the obstacles by sensor, and that is part of an autonomy. We will talk more about it in the next module. Okay. We will be sharing this MLX files, so it is easier for you to evaluate them. Now coming back to the lecture, we talked about scenario generation, the process of creating realistic, dynamic edge case environments so that we can evaluate the performance of the algorithm what we have developed for a specific mission or application. We can test UAV navigation algorithm, perception and control in this particular scenario. We talked about different type of scenario, static scenario, dynamic scenario, and we also talked about edge cases which is possible, which is very rare critical situations. For example, you can talk about GPS failure, or you can foliage comes into picture, and if the drone is not getting the GPS for a distance between let us say 10 buildings, right, how the controller going to work, or how much the drone is going to deviate from its path. Or we can even talk about emergency scenarios, how the drone is going to respond and visualize, or we can inject the winds in those scenarios and see whether the drone is still continue to track or not. All these can be evaluated, visualize the performance of the controller in a 3D world, right. We talked about different tools and techniques for this. Model in the loop, how we can model the entire flight control architecture. Then we can bring in software in the loop, and we bring in hardware in the loop workflows, how that will help us to validate the control law or algorithm that what you are developing, whether it is implementable in real time. The performance of the algorithm can be validated and visualized very nicely. One can use Simulink itself, or you can use Gazebo, or one can use Unreal environment to visualize the virtual environments, right. You can nicely integrate with the sensor modules like GPS, IMU, LiDAR, camera, right, so that you can just verify different autonomous stacks easily using scenario generator, right. We can also ensure safety, robustness of the algorithm. We can verify and visualize. We can look at the mission success when we talk about it for different applications, and various conditions in which how is our mission success, what is the percentage of success, how robust the algorithm is. All that can be validated easily using the scenario generation mechanism, okay. And it will help you to reproduce the real world or near real world. I will say there will be always a gap between the simulation and real. It is not going to be the actual environment what you sense, it is still a digital representation of the same, but you can still verify how close your algorithm with respect to the simulation world to real, and then you can see how good your algorithm generalizes to the real world. All that validation is possible once you do the experimental flight, right. That is beyond the scope of the course, but I am just trying to give you an overview how you will manage the part of navigation, which is very specific to us applications, and autonomy aspects comes into picture. The algorithm what you develop, can it be deployed in real time, and evaluation of the performances. Okay. Thank you.